no pressure then. Let me start the timer so that I don't steal too much of your coffee break. Yes, so first of all, I want to acknowledge the M-squared line project, which is the framework for this talk, and also colleagues at ECMWF. So this is a bit of a side project that I keep working on, and it's about correcting reanalysis. So if you remember, for early career scientists yesterday in Gunilla's slides, there was a big warning about using reanalysis over CIs. And yeah, this talk goes in the direction of doing something about that and trying to solve the problem. So in this slide, you can see our coupled model represents CIs. So normally we have discretization in multiple thickness classes. We have prognostic snow on top of this thickness class. And yeah, we have the concept of CI concentration. And I would argue that this is a quite realistic representation of the CIs, and it allows to simulate well the coupled processes. Now, if we look at a reanalysis model on the other side, we have a much simpler description of the CIs. So first of all, we don't have snow on top for most of them. We have a binary CIs cover, and we also have constant CIs thickness no matter of the season and hemisphere. And this brings issues. This is just an example. GRA assumes a 2-meter thick ice, ERA5 1.5 meters. And a very nice paper by Botrak and Müller showed that this representation in reanalysis brings issues with temperatures over the CIs, and in particular very warm biases in winter. So let's try to understand the situation. So normally, we have generally a positive temperature bias in reanalysis when the real CIs is thicker than the reanalysis constant CIs. In this case, basically the real world insulates more and should have as a colder temperature condition on top, while the reanalysis ice has a warmer surface temperature. We also have the opposite situation sometimes when the real world CIs is thinner than the reanalysis thickness, and in this case we have a cold bias in reanalysis. And yeah, let's have a look at the situation. So this is just a single snapshot. Here you have observations from satellites. So those are thermal measurements of the surface. Here we have the reanalysis field for ERA5 and GRA55. Here we have the daily mean. This is just a snapshot of the reanalysis. And yeah, here you see the difference, and you see that the biases are substantial and are mostly positive. And also we see that they are not constant in time and the space. So we know that they are prominent in clear sky conditions. And of course, I'm not the first one realizing this. This is a known problem. And actually, if you try to run a CI Sandocian model with those basically uncorrected reanalysis, you will not get enough CIs formation. And that's why typically the reanalysis forcings are climatologically cooled. So this happens, for example, in the OMIP protocol, or the Drucker project does the same for ERA interim and ERA5. And yeah, same is true for the NCEP reanalysis and the core reanalysis. We want to do a bit better, so we want to have a correction that's not climatological over the whole Arctic, but we want something consistent with weather, so that prevails in clear sky conditions. And yeah, we want something that also is aware of the CI's thickness below. So the idea is simple. So first of all, first step, we quantify the temperature bias, and we can do that because we have a lot of observations from satellites that are not assimilated in the models. Then, since we don't have observations for every reanalysis point, we need to have some predictors that we can link to this bias. And for predictors, we use reanalysis products themselves because they are always available, more or less, and we use atmospheric predictors, in this case the surface temperature itself, and the downward long-wave radiation, which is a good proxy for the cloud state, but also we also use reanalysis product for the CIs, in particular the CI's thickness from biomass and the snow thickness from the Lagrangian snow model by Liston. And then basically we have a model, that links these predictors through a fully connected neural network. It's a very simple machine learning model to this temperature bias. And once we can predict the temperature bias, given these predictors, we can also take the opposite, and that's the correction, basically, that we apply. There is one additional point, which is that we do this only in clear sky conditions. And this is because, first of all, we don't have observations in cloudy conditions, because since we are using thermal measurements, then the satellite just sees the temperature at the top of the cloud. And also, we know that these biases are stronger in clear sky conditions, so that's when the surface can effectively radiate heat to space and cool effectively. So yeah, there is a lot of masking and technical stuff going on with clouds. I'm not going into details, but yeah, if you're interested, we can discuss more. Now, let's have a look to some results. This is very busy, and I realize the rendering is not perfect, but yeah, let me guide you through this. We start with the bias on the top row as function of the atmospheric predictors here and of the sea ice predictors. And you can see that in general we see what we expect. For thicker ice and snow, we get a positive bias, and for thinner ice and snow, we get sort of a negative bias. Of course, there is a lot of noise. And the same, it's true here. We get a stronger bias for colder temperatures and clear sky conditions. And this is actually the signal that's captured by the machine learning models, so our correction. And you see that it reproduces quite well the structure of the bias. It also reduces the noise a bit, which is not necessarily a bad thing, but yeah, this tells us that this correction is just brings the system closer to it doesn't work 100%. You will see soon this later. Yeah, what happens when we apply the correction to a spatial map? So here again, same temperature that we saw before for the same day, the original ERA 5, and this is the difference now only for clear sky conditions. And this is the corrected field, how it looks like. So you see that in particular where it's very cold, we reduce the bias substantially. There are also regions where this strategy is not very effective, and there is also a bit of degradation in some regions, but I would say there is certainly a reduction where the bias is large. Of course, that was a snapshot, and we can now have a look at the average correction. So this is an average over a very long period, and we have ERA 5 on top and GRA 55 for different months. Of course, the summer is not included because in this situation we normally have a lot of clouds, and also the gradients are like the surface it's at melting temperature, so we don't really need that. Reanalyses get that, and we don't really need a correction. But we can see that the correction is strongest in winter, when the ice is thicker and it's colder, and it has a seasonality. And we also see that, particularly for GRA 55, we get this like double type of correction. So we have the cold temperature, the cold correction in the central Arctic where the ice is thick, but we also capture this warm correction over the thinner ice. And yeah, I think this is very nice, and you don't necessarily get that when you climatologically correct for these issues. And yeah, and you see that in particular in fall when you don't have a lot of snow, this positive correction manifests itself in peripheral seas in the Arctic. Okay, another relevant aspect is the seasonality. Yeah, I mean, we said we have seasonality, so the correction is stronger in winter, and by default, we don't have a correction in summer. But it's also nice to split these curves for different decades, and you see that the amount of the correction decreases with time. And this tells us basically, or my interpretation is that the current Arctic fits better with the 2-meter thickness approximation that Reanalyses do compared to the, let's say, the old Arctic, the pre-2007. And we see this very well in Era 5. The situation is not so obvious in winter for GRE55, but we see this in the fall. Okay, last slide. We had a look at trends, at warming trends, and we saw if the correction has an impact on the warming trend in the Arctic. Of course, we recomputed the anomaly compared to the new climatological state that we introduced, and we see that it induces sort of an acceleration, a slight acceleration in the trend. So the blue curve is a bit higher than the red one, but yeah, this is just, I would say it's a small perturbation compared to the signal, so we are not fully destroying anything. I think that's the message, and yeah. I will skip the summary, but yeah, I want to emphasize the next steps. So I would say this is sort of a version 1 of our model. We want to explore more predictors. In particular, we want to see if the wind can help the model by being a proxy of the stability of the boundary layer. And we also want to move from L3 satellite data, so daily pictures, to really going for on-track L2 satellite measurements. And in this case, we can have a very good consistency at the sub-daily timescale between reanalysis and observations, because at the moment we have reanalysis which have hourly time step or 3-hourly time step, but daily observations. And of course, you can do the assumption that in polar nights, the daily fluctuations are not so strong, but they are there. Yeah, there is a preprint available where you can learn more about this project, or you can drop me an email or contact, just stop me in the corridor at the conference. And I also want to emphasize that this is just part of the story, and of course operational centers are doing a lot of work in parallel to improve this issue with the missing snow and the constant sea ice. And this paper by Gabriele doing at ECMWF colleagues, it's a very nice example of that. So I leave you with this animation. I'm not sure if it starts or not. Yeah, where you see the correction applied to the hourly Era 5. And yeah, I'm happy to take questions if there is still a bit of time.
Thanks very much, Lorenzo. That was great. Couple of questions. Francois.
Hey, thank you very much. I had a question. So you looked at the mean state, you looked at the trends. Did you also look at particular extreme events like penetration of warm and moist air masses into the Arctic, where you expect the bias to be even larger? And did you look at whether the correction is effective in these particular synoptic situations?
I didn't look at moist air intrusions, and I know that probably since we mask cloud conditions, these moist regions will come with clouds. So our correction, it's not effective below clouds. We tried to use buoys data, but we were not as successful as with satellite data. So yeah, that's a bit, it's just half of the story, I would say.
Not directly, but related to your talk, like, do you know why the reanalysis don't do a better job of like treating the ice at the on the underside of their model? Because often, they, like you said, like they assume like a constant thickness. So why is it not more effort are being done so that maybe those bias would not be existing in the first place?
I think, no, I wouldn't say that effort is not being, I think there is a lot of effort from operational centers in improving this. It's just worked well traditionally. I would say still reanalyses are produced in atmospheric only simulations, so there is not a fully coupled system yet. And probably this climatological ice state was good enough for the moment. But yeah, of course, I think probably the next generation will solve these issues.
Am I correct to assume that when they see ice from satellite, they say 2-meter ice thickness, and then it's a constant thing? It's suddenly, there's no thermodynamic model being run, or there's no like slab ocean underneath, there's no...
There is a thermodynamic model of the ice. So there is...
But a fixed thickness.
But it's a fixed thickness, yes.
That's pretty poor, no? That's pretty simple.
Yeah, I agree. Yeah, that's why we're trying to correct it. But there is, I think, there are also I see a development in this, so this I'm sure will change.